In this video, we're going to go over section 4.5 from our textbook, which goes over absolute maxima and minima. So first, one of the most important applications of the derivative is to find the absolute maximum or minimum value of a function. And this can be used in a lot of real-world examples. For example, an economist may be interested in the price or production level of a commodity that will bring a maximum profit. Or a doctor may be interested in the time it takes for a drug to reach its maximum concentration in the bloodstream after injection, and so on. Okay, so this topic is very important, and so we'll start with recalling the definition of a local minima. So remember, if we have this point C, so f of c will be a local maximum if our function at x is going to be less than or equal to our function at this number c for x values near this point C. Okay, and then f of c is going to be a local minimum if we have that f of x will be greater than or equal to f of c for x values near that point C. Okay. Now, in this section, we're interested in finding the largest and smallest values of f of x throughout the domain of f. So in this case, that's going to be the absolute maximum and minimum values. So our definition changes slightly. If f of c is greater than or equal to f of x for all x in the domain of f, then f of c is called the absolute maximum of f. And on the other hand, if f of c is less than or equal to f of x for all x in the domain of f, then f of c is called the absolute minimum. And an absolute maximum or minimum is called an absolute extremum. Okay, so this changes our definition slightly from local extremum because in that case, we were looking at x values near C, and in this case, we're talking about all x values in our domain. Okay, so here are some examples in this figure here. Looking at the graph of this function, we see that we don't have any absolute maximum or minimum in this case, and this is because this function continues on in both directions. As you can see, all of our x values and our output values are going to negative infinity, and similar on this side, we're going to positive infinity. So we can't say for certain that one point will be greater than or equal than another for all x in this domain. However, for x values near this point and this point here, we see that we do have local maximum and local minimum here, and that's given by these guys here at -2 and +2. Similarly for this guy, we see that we do have an absolute maximum value because for all x in this domain here, we're not going to have a higher point or a bigger output value. And we can see this because all of our x values are going to increase in the negative direction and in the positive direction here, and all of our output values are just getting smaller and smaller. So in that case, this also tells us that we don't have an absolute minimum because all of our output values are getting smaller and smaller up to negative infinity. Okay? And then by the same reasoning on this guy, we don't have an absolute maximum here because all of our output values are continuing on in this direction, going to positive infinity. And then we do see that we have an absolute minimum because this will be the smallest point here at x is equal to 0. All right, so this brings us to the extreme value theorem. So a function that is continuous on a closed interval here has both an absolute maximum and an absolute minimum on that given interval. So this will happen when we have some restriction on our domain to some closed interval. Okay. So for example here, there are some cases, and it is important to understand that the absolute maximum and absolute minimum depend on both the function f and the interval ab that we're looking at. And so that's what we're seeing in these figures here. For example, we have this interval here from 2 to 12, and our function is given by this guy here. And so looking at this restriction, this closed interval, we see that our absolute minimum is here and our absolute maximum is there. However, if we were to change our interval, let's look at 4 to 10 now, our absolute maximum and absolute minimum values change. Okay, so like I said, it's going to depend on both the function and the interval. Okay? And then continuing this process, just changing these intervals, we see that the absolute extremum is changing. All right, let's look at this theorem here. So theorem 2 tells us that absolute extrema, if they do exist, must occur at critical numbers or at endpoints, right? So just looking back at this last theorem, these guys are our endpoints, this A and B. Okay? So this leads us to this procedure here, finding absolute extrema on a closed interval. So this is a step-by-step process. First, what we want to do is check to make sure that f is continuous over this interval. Then we want to find the critical numbers in this interval, and remember the critical numbers of a function are going to be the partition numbers of our derivative of that function. Then we're going to evaluate our function at the endpoints and at the critical numbers that we found. And the absolute maximum is going to be the largest value found in the previous step, and the absolute minimum will be the smallest value found in that step, in the previous step. So let's look at this example here. We want to find the absolute maximum and minimum of this function here on these different intervals. And like we saw in these examples here, the absolute maximum and minimum values will most likely change when we're looking at different intervals. Okay. So first, we want to make sure that our function is going to be continuous over our closed intervals. But something to note here is that this is a polynomial, so we know that this guy is going to be continuous for all values of x. For all values of x. Okay, so step one is done for actually all of these intervals here. All right, now we want to find the critical numbers in our interval. To do so, we're going to first find our derivative of our function and figure out where it is undefined or equal to 0. So the derivative of our function is going to be 3x squared minus 12. Okay, so just using power rule there. And notice that this is again a polynomial, so this guy will be defined everywhere. So we just want to figure out when this guy will be equal to 0. Okay, so then solving for x here. Our critical numbers are going to be plus or minus 2. So I'm going to start abbreviating our critical numbers as this here. So that is our critical numbers. And so now what we're going to do is we're going to evaluate our function at the endpoints for this first part A here, and at the critical numbers that we just found. So we're looking at this interval here. We're going to evaluate our function at those endpoints and the critical numbers. So this guy will be negative 65. Then at our other endpoint, this will be positive 65. And then evaluating our function at the endpoints, or sorry, at the critical numbers. We'll get 16 at negative 2. And then at positive 2, we'll get negative 16. All right. Going back to our procedure, the absolute maximum is going to be the largest value, and the absolute minimum is going to be the smallest value. So this tells us our absolute maximum value is going to be 65 here. So it's going to be the 0.5 comma 65. And then our absolute minimum is going to be our smallest value, which is negative 65. So that'll occur at negative 5, negative 65. All right. Now doing the same thing for part B here. We're looking at the interval negative 3 to 3. And notice that we already evaluated our function at the critical numbers in part A, so we don't have to do that again. And these critical numbers, -2 and 2, are in this interval. So all we have to do is evaluate our function at -3 and 3. So here we'll get 9. And then here we'll get -9. Right? So out of these guys and these guys here, it looks like at f of -2, we're going to have our maximum, and at f of 2, we're going to have our minimum. So our absolute max is going to be at -2, 16, and our absolute minimum is going to be at 2 and -16. And I'm slightly running out of room here, so I'm going to put this guy up here. All right. So this is our absolute max and absolute min on this interval here. And then for part C, we want to look at this interval, -3 to 1. So I'm going to evaluate our function at these endpoints. We know from part B that f of -3 is +9. And then plugging in 1 to our function, we'll get -11 here. And then something to note here, we have that our critical numbers are 2 and -2. However, the interval that we're looking at is -3 to 1. So something to note is that our critical number 2 is not included in this interval. So we're not going to consider it for an absolute max or minimum value. Okay? So we're just going to look at the endpoints here and the other critical number that is in our interval, which is -2 here. Okay? So then looking at these guys, out of these three, it looks like f of -2 has the highest value, so our absolute maximum is going to be this. And then our absolute minimum is the smallest value, and out of those three, it'll be f of 1. So -11. All right. Now, suppose we want to find the absolute maximum or minimum of a function that is continuous on an interval that is not closed. In this case, theorem 1 no longer applies, and we actually can't be sure that the absolute maximum or minimum value exists. And this figure here illustrates some ways that functions don't, or functions can fail to have this absolute extrema. So for example, here we know that our domain is -infinity to infinity. So this continues on forever in this direction and this direction, and we can't be sure at any point if there is any absolute extrema. Same for this guy here, we don't have a closed interval. And so although our function is not defined at f of 1 here, we could get closer and closer and closer to that value, and we don't know exactly what the smallest one could be. And similarly for this one, as we get closer and closer to this value, we're not exactly sure what the highest point could be. And then this guy here, we also don't know of any absolute extrema for the same reasoning as this one here. And this guy continues on and on forever in this direction and this direction here. So, in general, when we do not have a closed interval, the best way to find local extrema is to sketch a graph of the function like we've been doing in the past several sections. However, we'll see in this chapter that we can use the second derivative test to identify local extrema, which this will be very helpful when we don't want to draw the graph of the function. So that leads us to the second derivative and extrema here. So there are a lot of words here, but it's best illustrated with these graphs. So we're looking at the case when our second derivative at this critical number is going to be greater than 0. So we're looking at this graph here. So if this guy is going to be greater than 0, then it follows that this guy here, second derivative evaluated at x, is going to be greater than 0 as well, for x values really close to c here. So this tells us from the previous sections that if our second derivative is going to be positive, then our graph must be concave upward in this interval. Okay? And then this also implies that our derivative then will be increasing in the interval. And then since our critical number will make our derivative equal to 0, our derivative must change sign from negative to positive at that critical number. Right? And we'll see that that critical number is a local minimum. And so this is a sketch of that procedure here. So this is what happens when we have that our second derivative is going to be greater than 0. Okay? We have that our derivative is going to be negative on this side, so our function is going to be decreasing, positive on this side, so increasing on this side, and then we also have that our derivative is going to be equal to 0 at the critical point, which is our horizontal tangent line, and where we have our local minimum. Okay? And by the same reasoning here, when our derivative is less than 0, we're going to have a maximum here. So this leads us to our second derivative test. So if c is a critical number for our function, such that that critical number makes the derivative equal to 0, if the second derivative of our function is greater than 0, then that's going to be a local minimum. And if the second derivative of our function at that critical number is less than 0, then it's going to be a local maximum. So here's a little chart here to keep track of everything. So everything I just said is here in the first two rows. And then if we have the case where the derivative at the critical number is 0 and the second derivative at that critical number is also 0, the second derivative test does not apply. So let's do a couple examples here. We want to find the local maximum and minima for each function using the second derivative test. So starting with a here, what we'll do is first we want to find the derivative and the critical numbers, and then evaluate our second derivative at that critical number and look at its sign here. So first thing we'll do is find the derivative of our function. So we'll get this here. We know that this guy is going to be defined everywhere, so our only critical number is when our function is equal to 0. I'll just write it like this. Also something to note here is that in the second derivative test, our critical number that we're looking at in this case is going to be the one that makes our derivative equal to 0 anyway. Okay? So that's the only one we really need to worry about here. So we want to figure out when this guy is going to be equal to 0. So the first thing we'll do is pull a 3 out of this guy. And then we can factor. Alright, so then this tells us that our critical numbers are x is equal to positive 2 and x is equal to positive 4. Alright, so now we're going to want to evaluate our second derivative at these critical numbers. And so first, taking the derivative using our power rule, we'll see this is going to be equal to 6x minus 18. So our second derivative evaluated at the first critical point, we see that this is going to be a negative number. And then our second derivative evaluated at our other critical point, we're going to get 24 minus 18, so this will be a positive number. Okay, so these are our critical numbers just to keep track of everything. And then we have that our second derivative is going to be less than 0 at that point, and then greater than 0 at this point. So this tells us we're going to have a local minimum at this point here, and a local maximum at this point here. So what we need to do is find that local max and minimum. So first, we know that we're going to have a local max at this point here, so when x is equal to 2. So we need to evaluate our function at that point. And our function was that there. So plugging this in, we'll get 10 here. So this tells us we have a local maximum at this point. And then doing the same thing to find our local minimum. We know a local minimum is going to occur at this point using our second derivative test, since our second derivative is greater than 0 there. And then we'll find that point by plugging it into our function. So in this case, we'll get 6, and we know that we're going to have a local minimum at this point here. All right. Let's do part B here. So again, we're going to use the second derivative test to find the local maximum and minimum here when our function is equal to this guy. So the first thing we'll do is take the derivative of this. We know the derivative of e to the x is just e to the x, and the derivative of minus 5x is just going to be minus 5. So for part B, this is our derivative here. And to find our critical numbers, we want to figure out when this guy is going to be equal to 0. So we're going to just solve for x. So we'll take, actually, first thing we'll do is we'll add 5 to both sides. So we can get this here. And then now we need to solve for x. So we're going to take ln on both sides, since ln and e are inverses. We'll get x is equal to ln 5. And so this is going to be our critical number. And this actually is going to be our only critical number. Okay. And then we'll take our second derivative. So we're just going to take the derivative of this, which is just going to be e to the x. And then we want to evaluate our second derivative at the critical number. So plugging this in, we know that e and ln are inverses. So this 5 will come down, and this is a positive value. So using the second derivative test, this tells us that we're going to have a local minimum at that point. So we'll evaluate our function at this point. Our original function was e to the x minus 5x. We know that these guys will cancel, so we'll get 5 minus 5 ln 5. And then remember our property of logs here. If we have 5 times this log function here, this is the same as 5 minus ln 5 to the 5th power. And so evaluating this, we'll get this here. And this is roughly negative 3.047. So this tells us we have a local minimum at the point this here. All right, and the last example we're going to look at is this function here, part C. So again, first thing we're going to do is take the derivative. Using power rule, we'll get And then we want to figure out when this will be equal to 0. So the first thing I'll do is divide both sides of this guy by 60. So we'll get x to the 5th minus 2x to the 4th plus x cubed is equal to 0. Factoring out an x cubed, we'll get x squared minus 2x plus 1. All right, and then factoring this guy, we'll get x cubed x minus 1 times x minus 1. So this tells us that the critical numbers are x is equal to 0 and x is equal to 1. So now what we're going to want to do is evaluate our second derivative at those points. So first, finding our second derivative. Using our power rule, we'll get this guy here. And then we want to evaluate it at 0. Plugging 0 into this guy actually gives us 0. And then plugging 1 into this guy also gives us 0. And if you remember from our second derivative test here, we said that if that is the case, then we're not sure what the graph of f is and the test does not apply. So in this case, these are our critical numbers, and we saw that they both produce 0 when being plugged into our second derivative here. So this tells us that our second derivative test fails. And so what we'll do is use our first derivative test. And in the interest of time, I've already done that for us. So remember our first derivative test, I'll move this up. What we want to do is look at the sign of our first derivative. That'll tell us if we're decreasing or increasing. And then we know that when we're going from decreasing to increasing, we're going to have a local minimum at that point. Okay? So using the first derivative test, we can conclude that we have a local minimum at x is equal to 0. And then plugging 0 into our function will give us that point, and we find that it's 0. All right. Now this brings us to the second derivative test for absolute extrema on an interval. So if the function that we're looking at has only one critical number, then the second derivative test for the local extrema not only classifies the local extremum, but also guarantees that the local extremum will be an absolute extremum. So that's what this says here. So if f is continuous on some interval here with only one critical number within that interval, then if our if our derivative evaluated at a critical number is equal to 0, and our second derivative evaluated at that critical number is positive, then our function at that critical number is going to be the absolute minimum. And similarly, if our second derivative is negative at this critical number, then our function at that critical number is going to be the absolute maximum. Okay. This also means we have to be careful that the critical number can't be an endpoint, right? Because we're looking at this interval here, which is not a closed interval. So we'll look at an example here. We want to find the absolute extremum of these functions here on this interval. Okay. So we're going to use this theorem here. First thing we're going to do is find the derivative of this function. And then something to note here is that we can rewrite our function as this here. So that'll just help us to find the derivative easier. All right, so the derivative of this guy, we know 12 is going to be 0. the derivative of this will be minus 1. And then using power rule, we'll bring this minus 1 in front and multiply by this minus 5. So this gives us a positive 5. And then we have x to the power minus 1, minus 1. So minus 2. This gives us this here. All right. And then another way to write this will be minus x squared plus 5 all over x squared. You just combine those two with a common denominator. All right, so we want to find the critical number that'll make our derivative equal to 0. And we know that this function, the only way that this guy will be equal to 0 is if we have 0 on the top here, because 0 divided by anything is going to be 0. So we want to figure out when our numerator is equal to 0. And we see that this will happen when x is equal to plus or minus square root of 5. However, this guy is going to be our only critical number, since we said that each function was defined on this interval here. So minus square root 5 is not in that interval. Now we want to find the second derivative and evaluate it at that point. So what we'll do again is rewrite our first derivative so that it's easier to evaluate our second derivative. So we can just use power rule in that case. So then our second derivative, we know that this guy will be 0. This negative 2 is going to come down in front and multiply this 5. So we'll get a minus 10. And then we have x to the power minus 2 minus 1. And then this can be rewritten with positive exponents as this here. Now notice that when we plug in our only critical number into our second derivative here, we're going to get a negative number. So this guy is going to be less than 0. So this tells us that we're going to have an absolute maximum at this point. And so evaluating this, we'll get, just plugging this into our original equation. And this is approximately equal to 7.53. So this tells us that we have an absolute maximum at this point here. All right, and so we just concluded that using our second derivative test. We evaluated our second derivative at our critical number, and we saw that we got our second derivative was less than 0. And then since we only have one critical number here, we know that that critical number evaluated at our function is going to be the absolute maximum value of f on our interval. Right. So let's do the same thing for b here. We're going to take our derivative of our function, so we know the derivative of ln x is just 1 over x, and we have this constant multiple in front of that, so it's going to be 5 times 1 over x, and then the derivative of minus x is minus 1. And then this is the same as 5 over x minus 1, which is the same as 5 minus x over x, just getting a common denominator. And so again, we're just looking at when this guy will be equal to 0. And similarly to the last problem, this will happen when our numerator is equal to 0, because 0 divided by anything is going to be 0. So we want to figure out what will make this equal to 0, and we can clearly see that plugging in 5 for x will make this 0. And so this is going to be our only critical number in this case. So we're going to want to find our second derivative here. And again, I'll rewrite this guy as 5x minus 1 here, so it's just easier to take the derivative. So you know that minus 1 is going to come down in front, so we're going to have minus 5, and then we're going to have x to the power minus 1, so minus 2. And then rewriting this with our positive exponents, we get this here. Okay. Now we're going to evaluate our second derivative at the critical number. And this is going to be a negative number. And again, using our second derivative test on this interval, if our second derivative is negative or less than 0 for this critical number c, then our function evaluated at that point is going to be an absolute maximum. So evaluating our function at this point, this is going to be approximately equal to 3.05. And so this tells us we're going to have an absolute maximum at this point here. Alright, so that'll be it for this video.